This call is now being recorded.
Okay, right. So today we'll solve some problems based on week 5 content. We all know how a open loop control works, right? Just there will mm, there will be a system where its output will be C of t or y of t will take. And when it comes to closed loop control, we have a feedback. We have another element here that is a feedback, and it goes back here with the negative sign. Usually we used to take negative feedback since it is more stable than the positive feedback. And here comes another element when it comes to a closed loop control. In order to extract or get the desired response of the output, or whatever way the system whatever way we want the system to behave, we are including another element here called a controller, C of S. Let's take, and this G of S is the original plant. So the difference between this and this is, here it will, the output or the feedback will um, fed into the input from the output, right? The output is directly being fed to the system through input. So the this comparator will compare the input and the feedback, where the feedback is the combination of feedback element and the output information. Here there is another element which has been added here, that is C of S. It's a controller. It's a external element. We are adding it to pull the system to make it work in a way we like. For example, if I have a system like this, I'm taking a poles here, one pole here, another pole here. So in this case, I want my response would be something like this. My response would have some oscillations because one pole is in the origin. It might um, converge or it might not. That we are not interested right now. Since I have one pole which is at the origin, which make the system marginally stable. We saw that whatever wherever the when the poles lies in the left half of the S-plane, the system would be stable, and when it lies in the right half of the S-plane, the system would be unstable. Because inherently, if you have a pole that is S minus 1 and let's take S plus 1 and S minus 1. I'm just making a recap because we saw this before. When you take a inverse Laplace transform, you will get e power minus t. Here you get e power t, where e power minus t corresponds to a converging curve, and e power t is a exponentially increasing curve. It's an exponentially increasing. 1 minute, somebody message, I guess. Okay. Right. Say increasing curve. So this make the system stable where this is unstable. When you have a pole that is in between these two, just at the origin, that makes the system gives an oscillatory response. So in this case, I would get a oscillatory response because of the placement of this pole. So if you want to make the system stable from the oscillatory behavior. I don't like this behavior, but I want something like this converging behavior or a stable system. So I would need to pull this pole from here to here, right? I should make some adjustments or I should make some compensation such that I will replace or reorder the placement of the pole so that I will get the desired response. That's what this controller is going to do here. So this controller will compensate for this pole if one pole, for example, this is at the origin. If I put s minus or s plus 8, let's take. So this is my system now. For example, this is this system. So this will be 0 or this will be 8 minus 8. So in order, I don't want this little oscillator behavior in my system. So I want to cancel this poles and replace this pole at a different location. So what I would like to do is, in order to cancel this out, I will place another 0 at the same location. So I will place 0 at the same location. That cancel each other. This 0 and pole will cancel each other. This we call it as pole 0 cancellation. And we will add, in order to make the system at the same order, second order, I'm going to place another pole somewhere left. For example, s minus 5. So in this manner, I will pull the pole towards left. Minus 5 makes the system more stable when compared to the oscillatory behavior that we exhibit before, right? So how can we know where to place this poles? I can place it minus 1, minus 2, minus 3, anywhere in the left, right? Everything will make the system stable, but how much I have to compensate or how I am going to compensate, this we are going to see in this upcoming slides, like PI, PID controller. So how we want to, whether we want to place a pole or we want to place a 0, on what effects this will include into the system. That's what we saw in this week 5 lectures, right? So we are going to see in terms of problems now, the same concept. Anybody have any doubts here? Any comments you have to make? You would have seen the lectures, or you would have seen the previous lectures explained by the instructor. So if you have any doubts, please let me know here so that we can take forward with the problems.
No, ma'am, we can continue.
Okay, thanks. Okay. We have studied a concept called sensitivity here, right? So if we want to refresh on those topics, if we have a open loop system, for example, if we have R of t into G of s, and I have some y of t here. So if I'm putting a controller, for example, I'm taking a controller C of s and my plant is G of s as it is. Okay. And I'm adding a disturbance D of s. Some disturbance, external disturbance, I'm pushing or I'm to make the system unstable, or with some intention, I'm pushing this disturbance into the system. And I'm keeping R of t as input and Y of t as output. So then the output, this is my entire system. For example, I have a controller open in the open loop system, and I'm pushing this DS into the system. But there is a disturbance into the system. So my open loop output, how it will look like, Y of t or Y of s, I'm writing in S domain. My Y of s would look like R of s into G of s. So this R of s into G of s, and then, sorry, GC of s plus D of s whole into G of s, right? So this will be, as everything is in a cascade, this will become R of s, GC of s into G of s plus D of s into G of s, right? So open loop error would be, I'm calling this as open loop. My open loop error would be the input R of s minus of output Y of s. Just maintaining this as common, Y of s as common. So if I want to put this here, substitute this here, it will become R of S minus R of S into G of GC of S, G of S plus D of S into G of S, right? So taking R of S as common, this will give me 1 minus G of S into GC of S minus of G of S into D of S. This term as it is. Right. If I write the same transfer function in terms of a closed loop system, I'm just adding a loop here, which is closing the system with a negative feedback, unity feedback, let's take. So now defining the open loop system, defining the loop transfer function. Loop transfer function means this forward transfer function from here to here in a closed loop system. So that will give me similarly L of S is equal to just G of S into GC of S into G of S, because in the forward way only this two transfer function exists. So if I want to write it in terms of a loop transfer function, this in terms of system and controller, it will be G of S into GC of S, as both are in a cascade representation. Right. If I want to write a closed loop system feedback, it will be Y of S, but here just closed loop system, so I'm representing with YC. It will give me the loop transfer function divided by 1 plus loop transfer function into R of S. It's similar to G of S by 1 plus G into H, since it is a unity feedback system, unity negative feedback system. I'm going to replace this G with G into GC. That is the L here. If you have any doubt, please stop me then and there and ask, okay? Right. Now, I'm going to elaborate on this. Okay. Now, if I want to represent a sensitivity function, um, for example, the sensitivity function will map, this will map reference to error and shows how disturbance and model changes propagate to performance. Until the disturbance comes into the system, before this disturbance comes into the system, it was a very perfect system with this loop transfer function, only G of S into GC of S. Whenever we are including a disturbance, or we are considering there is some external disturbance acting upon the system, then this will affect the performance of the system. So sensitivity is a measure or a parameter that maps the reference, whatever input we are giving, to the error, overall error of the system, and shows how the disturbance or the model changes propagate to performance. So how well the disturbance is making the behavior of the system, making a changes in the behavior of the system or the performance of the system. This is the measure of the sensitivity term, is the measure of that. So the sensitivity function can be represented using S of S is equal to 1 plus 1 by 1 plus L of S, where L of S is equal to G of S into GC of S, loop transfer function. Whatever controller and your plant you have in your forward transfer function, that's your loop transfer function. Without having any feedback, without including any feedback, that's your sensitivity function. And there is another term called complementary sensitivity function. This maps reference to output instead of to error. This tells the relationship between the reference to error. This tells the relationship between the reference to output and shows how noise is transmitted through the system, or how noise is um, making the changes in the system behavior, right? This complementary sensitivity function can be written in terms of L of s divided by 1 plus L of s is equal to 1 minus s into s, where s is the sensitivity function we already defined. Both are same, right? You can write it either in terms of 1 minus 1 by 1 plus L of s, or it is L of s by 1 plus L of s. So whenever we want to see a relationship between, when some disturbance is acting upon a system, if we want to see the relationship between how the input to the error, the performance being propagated, then it denotes the sensitivity function. How the reference or input to output, the performance changes, then it refers to the complementary sensitivity function. I hope this is clear. If somebody have any doubt, I'll give you a moment to think about it. If you want to see few properties of this, for example, I'm taking a plant as G of S. If I have some changes to this plant as delta G of S, for example, I have a plant that works at 25 degrees Celsius, but I have some disturbance. I am opening my fridge and or I'm opening my freezer and let it open. And it is affecting the room temperature. The freezer's air is affecting a room temperature. It's unlikely, but I'm just keeping it for reference. So this nominal temperature of my 25 degrees Celsius of my plant is getting changed to maybe 23 degrees Celsius or something. Okay. So this is the difference in my plant operating temperature. So I'm taking this as a delta GS. I'm considering this as a delta GS. So when it comes to a sensitivity, particular in terms of closed loop sensitivity, if the plant changes by delta G, if the plant behavior changes by delta G, the closed loop sensitivity of the loop transfer function, where loop transfer function is the G into GC, to plant variation, this to delta G of S is reduced by 1 by 1 plus L into yes. So since it has this L of S is in the denominator, when we have a gain L, or the loop gain of your G into G of S is very high, that is greater than 1, the delta G will be attenuated, right? So when you consider adding a pole, for example, if I add a pole, how this will affect the system. Adding a pole or integral action, this increases the system type, where type is the number of poles at the origin, right? System type, and it will eliminate this steady state error. Right, but this will be applicable for some input classes like step ramp only. Right. Then when I'm considering the increased loop gain here, for example, if the loop gain is very greater than 1, this increased loop gain at low frequencies, for example, low frequencies, to attenuate low frequency disturbances, reduce the loop gain at high frequencies. So when we have a loop gain or greater loop gain at low frequencies, this reduce the loop gain at high frequencies. This loop gain will be smaller at high frequencies. This is being done to avoid the amplifying noise or amplifying measurement noise. So these are some of the properties or something we have to look upon this. Moving to an example, I am considering a thermal plant where G of S is equal to 1000 divided by S plus 1 into 10S plus 1. Okay. Where I'm having R of T is equal to a ramp of slope 30 degrees Celsius per second from T0 to from T equal to 0 to 30 seconds. Which recording, Ashmin? Which recording are, is said to be uploaded? Today's session. Okay, yeah. After this session, we will upload. Oh, okay. There is some issue in uploading this session, right? The problem is it is taking a little more time, more than half to 1 hour to for rendering the entire session. And after that, we are we are going for different work and we are missing to upload this session. And we will make sure it won't happen and we will try to include as soon as possible. Okay. Okay, right. Back to the problem. We are considering a thermal plant where the input is considered to be a ramp of slope 30 degrees Celsius. For example, your input should look like this. Say ramp input where the slope is the 30 degrees Celsius per second. For every second, the slope will increase every 30 degrees Celsius. Okay, with a constant comment u. Then at it goes to 300 degrees Celsius after 30 seconds. So until it reaches a 300 degrees Celsius, it increase 30 degree every seconds and after that it will go to 300 degrees Celsius constant. After that it won't change, right? After 30 seconds. So this is my plant G of S where G of S is mentioned here and I have a ramp input R of T and I am expecting some output Y of T. So this is the information I get from my input where my input comment or the input signal would look like this. So it will increase until 30 seconds, 0 second, and it becomes stable to 300 degrees Celsius after 30 seconds. Until it increases at 330 degrees Celsius per second. So this is the information we get from our input. Sorry, from the given thing. First, if you want to find the steady state error, no, slope is 30 degrees Celsius. I'm considering 30 degrees Celsius here per second. The idea behind here is, so as we have a little ramp input and we have a step. So this is a combination of ramp and step, but ultimately this is settling at 300 degrees Celsius, right? So if you want to find a steady state means we have two types of responses. One is the initial response until it reaches one steady state value, that is we call it as transient response, and after it reaches we call it a steady state response. So here, if you want to get a minimum steady state error, ultimately, if whenever we design a controller, our objective will be twofold. One is the system should give a desired response, and the system should exhibit good transient and steady state behavior. In the sense, first one, you know that if you want to if you want the fan to rotate at 200 rpm, if it rotates at 200 rpm, then it is working as per the desired response. But in terms of transient response or the steady state response, we have different criteria around it. For example, when it compared when we consider only the steady state response, we always want the steady state error to be zero or nearly to be zero. So this represents the system is behaving good, and if there is no steady state error, the system ultimately works on your desired performance range only. So that is the understanding. So these are all one-to-one connected, right? Now, if you want to reduce the steady state error, and since we have a stable value here, we would go with the DC gain, some constant value we can choose. But for a time varying reference or a disturbance, if we consider, the open loop approaches will fail. So it will give a large tracking error when references changes or if there exists any poor disturbance rejection. So we go with a closed loop. We are going to introduce a controller that is a proportional controller. I'm considering for now for simplicity. We will see whether it is enough or we want to add some integral or derivative actions along with this. Right. So I'm going to start with the since we are in the initial step, we are going to do step by step. So I'm going to consider a proportional controller first. So if I consider a proportional controller, g of s would be kp. One gain will be added here along with g, and we have a h of s to this. So g of s, we know h of s is considered to be 1. It's a negative unity feedback system, let us consider. So the closed loop transfer function will look like something like this: kp into g of s divided by 1 plus kp into g of s, right? Any doubts or anything out of this? Nothing, right? If you have, please not stop me then and there. Right. So for a steady constant reference, that is 30 degrees Celsius per second and 300 degrees Celsius after the ramp finishes, the steady state output for step response, the steady state output for step reference, the steady state value I'm considering. So that should be R of S is equal to 300 by S. Since it is a step reference, I'm considering 1 by S and the settling value is 300. So it is 300 by S here. So your error, steady state error would look something like this: 300 divided by 1 plus Kp into G of 0, where I'm substituting S is equal to 0 here. So it is G of 0. Wherever there is a S in G of S, that should go to 0. So this will give me 300 divided by 1 plus Kp into limit S tends to 0, 1000 by S plus 1. Okay, where it is into 10s plus 1. Okay, right. Now this will be 1 plus Kp into, if I put S is equal to 0 here, it will 1000 divided by 1, right? So now this will give me 300 divided by 1 plus 1000 Kp. So this is my steady state error. So based on the Kp's value, the steady state error will change. With considering Kp to be very low, for example, Kp is equal to, I'm considering 0.01. Since there is a 300 there above, I'm going to consider 0.03 for it will be easy to cancel. So it will be 1 plus 1000 Kp is equal to, it will give me 31, right? This 300 and 0.03, if I take constant, it will give me this. So this, if I take, this will give me 300 by 31, around 9.7 degrees Celsius it will give. For example, I'm considering to be, I'm rounding it to 10 degrees Celsius, right? This is for steady state error. And for RAM, I'm going to take, that is for first 0 to 30 seconds. It will become a type 0 system, right? Because there will not be any integrator. So as my entire G of S has, G of S is S plus 1, 10S plus 1. Okay. G of S is equal to 1000 divided by S plus 1 into 10S plus 1. Right. So for the first 0 to 30 seconds, there will not be any integrated because I'm considering only the proportional controller. There is no S here. So it will be a type 0 system. When I substitute this for the ramp input, and if I find a steady state error for a type 0 system with ramp input, it's going to give me a infinite steady state error. We know that from the table we saw in the previous week, right? So this, considering this, your ramp tracking is poor. Right. I don't want any infinite steady state value. This is very bad. And here I'm getting somewhat near, not close to 30 degrees Celsius, but somewhat I'm getting some finite number. But still, I need to improvise on those. And the tracking error is very poor. For example, your system or output response won't settle at all. The steady state error infinite means your response is going somewhere when the time tends to infinity. So it is not, there is no point in doing this proportional controller alone. So let's try with adding one integral controller. For example, if I consider same Kp plus Ki by S. So I'm adding an integral controller along with the proportional controller I have introduced. So if you have any doubt in how this Kp by S comes and how, what the nuances behind this Kp, if you have any doubt, please let me know. It was discussed in the previous lectures and in the videos also. We can also discuss it here again. So when I consider an integral controller, this PI or a proportional integral control introduce an integrator so that this closed loop system, your closed loop system, when you consider 1000 by S plus 1 into 10s plus 1 is your open loop, right? So when you write it in terms of a closed loop, this will become g of s by 1 plus g of s into h of s, where h of s is 1. I'm going to leave it as it is, g of s. When you write this and when you consider the r of s here, and this g of s will be gc of s also. Another gc of s would come, where this gc of s has 1 by s, this proportional action here, right? So this will make, this will be, this will come here also. So this will make the system type 1. For example, the 1 by s in the numerator will come here. It becomes a pole at the origin. So this will make the system from type 0 to type 1. And it eliminates the steady state error to a step and can track ramps better than depending on the gain value we have chosen. For example, if you choose the same value kp equal to 0.03, I'm taking the as the whole value, and I'm considering ka also nearly but little lesser than the kp. It should not be more dominating because it may introduce a integral wind up action, right? So I'm going to start with a very low value since it has 300, like if I want to track 300 degrees Celsius, I'm going in terms of 0.00303 and all. If it is 50, I will go with 0.05 kind of. It will be easy to calculate by hand. So if we consider this and if you plot it in the MATLAB, it will reduce the steady state error and it will enhance your faster settling time also. So I would prefer this PA controller for this type of system. So if you want to use MATLAB, I have, but I don't want to switch between that. If you really want to see, I can do that. So in MATLAB, if you can write it in terms of S is equal to transfer function of s and write this g of s, whatever g of s we have, the 1000 divided by and all. And gc of s, consider kp plus ki by s, where kp you take from 0.012, 0012, 0.03, and K also you try changing from 0.1, right, to 0.03, and K also you try changing from 0.0001 to 0.003, and make a plot, use LSIM commands to make a this x-axis with time divisions. For example, you can take 0.01 seconds or zero point 0.1 seconds, whatever way you want. You split the time using the LSIM commands and then plot the output response of your system. Whatever way you call, whatever name you call output, or some variables you used to call, right? See, with respect to t, whatever here you would have defined the t here, t comma c. You plot this and see how well the steady state error is getting closer to the reference point when compared to keep first just keep only the kp, then try with one kp and ki, and you might see the difference between these two. Any doubts so far?
Just can you slide up? I have to note down. Yeah.
290 is also valid. Earlier, if it is 10 degrees Celsius here, if it is 10, we would have chosen 0.01. Then this will give me 10, 1 by 300 by 1. So, or same 300 if we take, it will be 10, 1 by 1 plus 10 kp is equal to this 31. That will be 290. Yes, it would be. Yeah, it will be valid. I'll quickly post a question. You try to answer that. Okay. Please answer in the chat box. Derivative control improves steady state error, reduce overshoot, increase overshoot, increase the stability of the system. Can you analyze the understanding of each and of the derivative control when we will introduce a derivative control into a system, and what is the use of that? Based on that, how what will be the effect of a derivative control? Take a moment, think about it, and explain it. You can type your answers in the chat box. Do you need help or do you have any questions around this? Why it is taking a long to answer?
Ma'am, 1 to 4.
1 to 4. Okay. You have chosen 1 to 4. Right. Anybody have any different opinion? Or you want me to revisit the topic a little bit if you are getting confused here? If you tell something you think, then only I will be able to explain accordingly. So please respond. Okay, review would be helpful. Thanks. I will take a review. So we have three different control, right? Initially, so as we saw in that introduction session, previously we only correct the control system using the feedback. That is a closed loop system feedback. And later in this week, we have introduced another element into the system that is known as controller, external controller, which changes the poles or zeros of the system so that we will get the desired output response. This is the idea behind introducing a controller. The controller can be of three different types according to this week. And the controller, we have numerous types of controllers, but in this week we are going to see only this three different types of controllers: P, I, and D. P comes for the proportional control, I comes for the integral control, and D represents the derivative control. Right. So this proportional control, what it will do is, first of all, before going this, I want to know what is error here. Error is the difference between the input and the output, Y of t minus R of t. So this is how we define a error in any system, right? Whatever input you give, if the output comes corresponding to that input, then there will not be any error. There is no issue. We don't have to make any corrections. But if those two are not in the same manner or in the same mode, so we will introduce something else externally to make the correction. That's what we are going to see now. So when we use a proportional controller, so in a system, this is R of t, we call it as R of t, GC, and G, it's a plant output, and we have H. So we are familiar with all these terms. There is one external term that we are going to use is U of t here, where the difference, we call this two as input. What is the difference between U of t and R of t here? The U of t is comes from the correction here. The input to the plant, the actual input to the plant, actual after the controller correction is U of t. But the reference, whatever we give is the R of t. So don't get confused between this inputs terms. Whatever reference we want the system to follow, it is R of t always. And whatever input that is coming or output that is coming out of the controller that is being fed as input to the plant, that we call it as Y of t. Clear or confusing? Y of t lies here in between your plant and your controller. Controller's output, plant's input, that is Y of t. But the reference we always want the system to track is R of t. We also call this as input sometimes if there is no controller. We use this interchangeably. Okay. Now, if I am using a system G of S and I want to introduce a controller GC of S, I have an input U of t here. So this U of t, if this controller is a proportional controller, then this U of t will look something like this. Kp into E of t, where Kp is the proportional constant and E of t is the error. Again, it is the difference between the output and the reference input, right? It's a simple proportional controller. So what the intuitive thing behind this is the control effort. We call this input as a control input, right? So this control input or the control effort we take will be proportional to how far we are from the target. For example, if my reference is 10 and if my system gives an output 8, then my constant would be proportional to this error equal to 2, right? So larger this error, larger or stronger will be my proportional constant. My Kp will get increased proportional to the error we have in my system. I hope this is clear. So it's like a spring. For example, it's like a spring pulling the system towards the set point. That's it. We are tightening the spring or making the adjustment to the spring. So what this actually does is to the system in terms of a transient response or steady state response, this reduces the rise time because as you are making a correction that is proportional to your error. This pulls this, if the previous response was like this, it pulls the system closer or making it faster. So your rise time will shift from here to here, right? So it will change proportionally according to your error. So larger the error, this it will pull the rise time to the left or reduce the rise time. I'm sorry, this will be like this. Rise time is here, right? Yeah, it's right. This will be TR1 or TR2. TR2 will be lesser than TR1 because if you use a proportional control. Then it reduces the steady state error. The core idea behind using this proportional controller is to reduce this steady state error between this. So when you introduce a proportional controller, this will try to come like this. And when you introduce another proportional control, it will try to come like this. Sometimes there is a disadvantage. As the advantage, there might be disadvantage also. It may go beyond the limit. For that, we will use different actions. Next, different integral or control actions. Seeing from the proportional control point of view, it will try to bring the steady state error closer to zero. So it is reducing the steady state error. The problem is whenever the error is very large, it tend to increase the oscillations or stability. That's what I explained lastly. So if your system has a larger steady state error, for example, this is 10, then your gain will also be proportional to 10. All of a sudden, if you pull the system from one point to another point, which is a very large set point, then this may push the system into the verge of the instability. This is one disadvantage of the proportional controller. So when we can use this proportional controller, if your system is already stable, then it is safe to use a proportional controller. The proportional control won't make the system from stable to unstable because it is not introducing any zeros or poles, or it is not disturbing the location of your poles of the system, because we are not adding any S to the system, right? So it won't change the stability nature of the system, and you can use this whenever the steady state error is small and acceptable, or it's very simple. Otherwise, you have to use this proportional controller with combination of other controllers. Any doubt in proportional controller so far? Any part you didn't understand? Please let me know. Make it an interactive session. Otherwise, I don't know how well you are able to get it.
Ma'am, what you wrote TR?
Ah,
Transient, this
transient response.
transient response. Okay.
Ah, You're asking what it will do for the transient response.
Yes.
Right. The transient response, when compared to other categories or other parameters in the transient response, it largely affects the rise time in the system because it won't make any changes to any settling time. Largely, maybe very small changes it might happen because of it is pulling the response to the left, but largely it affects the rise time. And in which ways it reduces the rise time. In transient category, I will just write it here. In transient category, it reduces the rise time. In steady state category, it reduces the steady state error. This is the behavior of a proportional controller in general. And it might change a little bit based on the gain value you consider. Okay. In general or on whole point, this is the common nature of a proportional controller alone. It's clear? Okay.
Yes. Okay.
All right. If so, we are moving to the next controller. I'm hoping that you understood. Right. When it comes to the integral control, we are going to add the same controller, but in terms of another one variation, I would say. In that manner, your control effort or the control input would look something like this: Ki integral 0 to t e of tau d tau, where your e of tau is the error that varies with respect to time. In S domain, if I want to write integral action 0 to t, if you differentiate it and take a Laplace transform of this would give me E of S, or I will keep, maybe it
Upon
will,
S.
I will keep it in time domain itself because I want to keep it proportional controller. I kept it in time domain, right? So I will just write it like this: 0 to t dt. Okay. When you want to write in an S domain, it will be K by S, Ki by S. Okay, that's okay. Now, when we see an intuitive understanding behind this, it accumulates the history of error. If the error persists, the integral term keeps increasing until the error disappears. For example, if the first, when you apply a control action, for example, at the first iteration, I'm taking first iteration, I'm applying one reference for my reference is 10 seconds. So I want my system to track this 10 seconds. My reference is 10 seconds. I want my system to track the 10 second, but unfortunately my system is tracking 8 seconds. Okay, this there is a steady state error between these two as a 2 seconds here. So at the first iteration, my error would be 2. So I'm applying a control action again. I'm making some changes. I'm giving some input proportional to this one control unit, whatever control unit you have, RPM, voltage, whatever control unit based on the system. I'm just writing in terms of number without any unit. Okay, the reference would be the same, but I'm expecting the system to behave in a different way. It behaved a different way, but it just increased 1 seconds. Now previously it was 8, now it was 10. So now the error is 1, right? Now the error become 1. In the next control action, I'm going to keep the control action as it is because there is no much change. So after the second iteration, I expect the system to work in a different way. It worked same and comes to the 10 seconds. So now the error becomes 0. So when you see the control action, if you consider only the proportional controller, this is considered at that instance. For that instance, the error will be 2. So the proportional constant will change proportional to this 2. And at the second iteration, it will reduce because the error is getting reduced. At the third iteration, there will not be any needed for the proportional controller action. It will be 0 because the steady state error has become 0. So this is how proportional controller works. But when it comes to the integral controller, this will be added together. So eventually when your error is getting reduced, your control action or your ki will also get reduced. This is error and this is your ki. If your error keeps increasing over time, accumulating this error makes the ki will also increase over time. Do you understand this relation? So when it comes to a integral controller, it accumulates error over time and produce control gain or control effort proportional to the accumulated error. This is particularly very useful when the proportional controller, whatever value you use, the proportional controller couldn't increase or reduce the steady state error to zero. So whenever sometimes this proportional controller alone cannot make the system comes to zero steady state error. There will always be a steady state error because it has been changing proportionally, right, from one point to another point. At one moment it won't be able to, after some iteration, some finite iteration, it won't be able to bring out the steady state error at all. So at that point, this adding this integral action would help. This integral action will bring down the steady state error to zero more definitely than the proportional controller, because it is accumulating the error over time, right? So it keeps tracks of the history of error that has been occurred in the past also. So it is going to change accordingly, not just based on the that moment or that constant error. So it also improves disturbance rejections. It will be able to eliminate the what do you call it? Eliminate the whatever effect the disturbance causes in the system. This will be able to eliminate those because same thing, it accumulates error, it also accumulates the history of disturbance happened before, so it generates a control effort accordingly. So it will be able to reject the disturbance properly when compared to other controllers. The problem here is there will be disadvantages as we see for proportional controller. I said before that your as your error increases, your ki will also increase, right, over time. So when the error didn't get reduced, some point of time the ki tends to go to infinity. So at this point, we won't be able to control the system, and since the ki is uncontrollable, using the same ki in the system will make the system to grow from stable regions to unstable region, because yes is at the origin, right? S is equal to 0, your type 1 system will be at the origin. So keeping the poles at the origin and increasing the gain alone to infinity, it will make it dangerous. It push the system from this verge of instability to unstable region, or instability, make the system unstable, okay. And it also creates, it may create a slower response when it sees from the transient response side of view, and it increases the overshoot. These are little disadvantages of integral controllers only if ki is too high. So when in this case, it may introduce a overshoot into the system, and that this scenario we explained here, right? This is called as integral wind up. The integral action keeps winding up, keeps increasing and not able to let it out. This is the problem with the integral controller. If you use only the P and I or only the I, you may see this type of disadvantage here. Any clarification needed in integral controller? Please respond, use a thumbs up or something.
Ma'am, first discuss derivative, then then we will.
Okay, right. Okay. Then, okay. Derivative control. So similarly, derivative control efforts would look something like this: KD into d of t by dt, d into e of d by dt of e of t, where we are differentiating the error over time as we did integration before, right? It's a just a opposite nature action. So there was a disadvantage there, no integral wind up. So the error keeps getting increased. So your ki will also get increased. There is no way to bring it down. So this derivative action is being introduced to eliminate one of the disadvantage of this integral controller. This is the opposite of the integral action. So it will help us to bring down the integral wind up little bit or more than that, like effectively when we use a derivative control. So all this kp, ki, kd are the constants where the next terms will depend on your error. Where in proportional control it will just change proportionally. In integral controller it keeps tracks of error, it saves all the error and the changes accordingly. In derivative control, instead of integral it will take a derivative of error, or it tries to reduce the complexity of the error over time, and it will make a control action accordingly with respect to the derivative control action, right? So the main idea behind this is it reacts to the rate of change of error. So however your error's rate of change your error changes over time, it will generate a control effect based on that, right? When error changes rapidly, derivative produces a strong opposing action to prevent the overshoot. What it has been caused using the integral action. So it's just a mirror image of the integral action. So because of this, you can eliminate. You can first improve the damping. Like this indirectly improves the transient response. It brings down the overshoot, just opposite of integral, whatever you learned there, and it increases the settling time. There it creates a slower response, right? So this will create a increased settling time because like faster response. And it stabilizes the oscillatory behavior exhibit using the integral action of the system, right? So when you use a PI controller and your error is not getting reduced, then we can consider going with PID also, increasing the D. With the PI, if you are getting a stable output, then that is enough. No need to go to D. And if even if you get a stable response, but your settling time is very slow and you are expecting very slower response out of the system, then also you can go with PID controller. And as usual, there are some limitations to D also. So it might increase the noise of the system, or it amplifies the noise that has been there already. And implementing this is little bit difficult when it comes to the we have to implement it as a filtered derivative. KDS divided by 1 plus tau s. We have to implement it little differently than that. It should be of a filtered derivative, not a direct derivative. So when we want to compare all this, I am taking P, I, and D. So your control action would be U of t. I'm going to write, right? So it will be Kp into E of t. This will be Ki into integral E of t dt. 0 to t is the limit. And this will be Kd into E dot of t, where E dot of t is d by dt of E of t. And this rise time wise, when it comes to the transient response, rise time TR, this reduces the rise time, and not going to affect rise time much. And overshoot, this is another important criteria, and transient response. This will increase the overshoot. It might increase the overshoot, or this will definitely increase the overshoot, and this pulls down the overshoot. In terms of steady state error, steady state response, it's a steady state error. This reduces the steady state error. It eliminates the steady state error, and this won't do much in steady state error part. Okay. In terms of noise sensitivity, this reduces noise. This reduces noise. This is the only villain in the noise part, derivative actions. So if you want to do a basic correction, go with proportional control. And if your steady state error is not going to zero at all after too many iterations, then consider going with integral. And if it increases your overshoot, or it is creating a very slower response, or if it makes the system unstable, then consider adding the derivative control also. Other than that, sometimes you don't even need integral action. You can go with the P and D. So if you have D is not going to do steady state error, not going to affect steady state error anyway. But if you want to reduce the overshoot with the proportional control, then you can consider going with the derivative also. P and D kind of, you can go with that. Right. So coming to the point where we started off with this question, right? So now can you see what actions, like what are all the options would be suitable here? A derivative control, will it increase or reduce the steady state error, overshoot, stability? What do you think would be suitable one?
It will decrease the overshoot, and
Uh-huh.
option 2 is correct. And steady state error, it will not affect steady state error.
Yeah,
And stability, I
exactly.
guess 4 is also right. Yeah, stability is
Yes.
also increased. Yeah.
Yes. Or and everybody else is agreeing with this? Do you have any doubt or any problem with it? Okay. 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 Manoj, you also okay with this, right? Okay. We'll try to solve some more problems. Consider a plan with the transfer function g of s is equal to 1 by s into s plus 2 with the unity feedback system, negative feedback system. And I'm going to add an integral control k by s. The closed loop system would be zero steady state error, finite steady state error, is marginally stable, unstable. So I have given a system where it's one of its pole is at origin, another pole is at -2, and I want to add an integral controller, and I'm asking what this adding integral controller would do. Please think and let me know. We have seen, no? What this integral controller might do. Will it make the steady state error zero? Considering the closed loop system, write the closed loop transfer function with this and then try to analyze with that. Will have a finite steady state error, or it will be marginally stable or unstable.
Option A.
Will it make a zero steady state error?
Means
Okay.
nearly to zero, not means approximately to zero.
Okay. Okay, right. You're saying if we add the integral action, it may make the system steady state error to zero. Okay. Do we have any other options or any other answers other than this?
Or might be finite, but finite would have been derivative. So
Mm-hmm.
option
Okay.
A, option A is better than option B.
Rest of the options. Okay.
Uh,
Let's try analytically. 1 by s into s plus 2. You see, there is another pole sitting at the origin, right? And we have GC of S, that is also a pole sitting at the origin. Now, if you want to write a closed loop system, it will become K by S, G of S into GC of S will come in the top. 1 by S into S plus 2 divided by 1 plus K by S into 1 by S into S plus 2. So now this becomes K by S square into S plus 2 divided by S square into S plus 2 plus K. And this will get cancelled. This will be K by S square into S plus 2 plus K. Let's make the system S q plus 2s square plus K equal to 0. So if you see, this becomes s square plus 2s cube plus 2s square. There is no s term, 0s plus k equal to 0. So now based on this k value, we can say the system might be stable or unstable, right? Since this term is missing, if you find the poles for the system, you would know the system would be unstable. So that's why whenever you are seeing a system, try writing the system in terms of the closed loop system first. Using the closed loop transfer function, come to a conclusion. Okay. Right. So this will make the system unstable. Rather than discussing the steady state error, this system is inherently unstable. There is no point in seeing how the steady state error would look like, right? It will definitely be infinity because since the system has an exponential output, uh, whatever reference you give, it won't track. It will also be infinite. Okay. Can we solve one problem from previous lectures? So it will be useful for this week also. So consider a system g of s is equal to 60k by s into s plus 6 into s plus 2 with k equal to 1 and find the velocity error constant of the system. That is kv. Okay. So I'll just give kv. We know that is limit s tends to 0 s into g of s, right? So g of s was given here. Can you work it out and let me know the answer? It's straightforward. This limit s tends to 0 s into 60k by s into s plus 6 into s plus 2. kv also kv was asked to find.
5k would be the answer. KV equals to 5k.
KV equal to 5. Okay. Everybody
5k.
getting this answer?
K
5K.
equals to,
K
k
equal
equals
to
to.
1 it is given. No problem. Okay. Right. Now, for the same system in this question, 60k g of s is equal to 60k divided by s into s plus 6 into s plus 2 with k equal to 1. Right. Suppose I want to add a 0 on a real axis to the open loop transfer function at location, some random location s is equal to minus left half of the s plane. I want to add a 0. What should be the value of z such that the closed loop system with that 0 has a peak overshoot of MP percentage of 44.7 percentage? Got the question? So I have a system G of s which is 60k by s into s plus 6 into s plus 2. The question suggests I want to add a 0 at s equal to minus z. So I'm writing in terms of s plus c. Right. So I want to find the z such that my closed loop system gives an overshoot of 44.7 percentage approximately. Can we find it? First, write the equation for the overshoot, peak overshoot. E power minus zeta pi by root of 1 minus zeta square. Try finding the values for this. So if we want this, okay, this is a third order system, right? So it will be difficult for you to find by hand. Can we use MATLAB? You're okay with MATLAB, like familiar with MATLAB? How to find this? We have done few exercises during the previous weeks, no?
Yes, we can.
Yeah, right. I will share my screen. Going to use and 60 and 60 into s plus 1, right? S plus z. So I am going to first consider z is equal to 1 for now. U equal to u 60 and 60 into Z, whatever I am considering, comma, your denominator would be, if I do this S into S plus 6 into S plus 2. So this will give me, if I find a closed loop transfer function of this, S square plus 8S plus 12 plus 60, 72. Right. Okay, this will be 1A. I'm writing closed loop transfer function into Z. Okay, this is my entire transfer function. Now I want to see if the step response of the system, because I want to see the peak overshoot, right? So the command to do this is step of transfer function 1. Getting generated. Okay, so this is my step response. If I see this, this becomes 1.13 instead of spending time here. It's just another comment that is step info. This will give me all the transient response specifications. So if you see this, here the overshoot is 13. Okay. Let us just increase the proportional constant that increases the overshoot. Um, then your transfer function will change. It also keeps overshoot same. No, sorry, I increase the k, no? Z, I should increase. C2, it pull it to 26 from 30. If we keep increasing, it might go to 44, but there is another proper way to do this. You can write a code to equate this and find it by solving this equation. Then it will straight away give you the value for Z. Why I keep changing key? Okay, now the overshoot becomes 3.8. So if I put k equal to 4, sorry, z is equal to 4, 48 it becomes. I want 44, right? So I'm going to consider z equal to 3.8. It is also taking time, right? Z is equal to 3.8. It becomes 3.6, 44, right? So when z is equal to 3.6, it becomes 44. I think that is a proper value. Okay. Now your z should be 3.6, so that you will get the desired peak overshoot as 44.7 some around, exactly around 44.7. Okay. Can you now find the velocity error constant of the system after adding this zero? kV equal to 1, where S is equal to minus 3.6. Sorry, Z is equal to minus 3.6. The 0 has been added to S plus 3.6. And consider K equal to 0.5. Instead of K equal to 1, consider K equal to 0.5, where your G of S is equal to same 60K by S into S plus 6 into S plus 2. K equal to 0.5 and add a 0, that is 60K S plus 3.6. We found it from the previous section. Okay. Can you find KV? Limit S tends to 0, S into G of S. Please solve and put it in the chat box. Nine. Okay. Anyone getting different answers? K is 0.5, right? 3.6 by 6 into 2. 2.5 into 3.6 would be around 10, around 9 point something. Nine, right? Okay. Everybody's getting same answer. Okay, we'll go ahead with another question. So if you add the 0, S is equal to Z instead of minus Z. Next question is, this is question number, okay, I lose track of question number. If I want, previously I added S equal to minus Z, right? Now I'm saying I want to add S equal to Z with the same Z we found before, that is 3.6. Can you find whether the closed loop system is stable or not? Putting S is equal to 3.6, because it will be 3 S minus 3.6 into the whole G of S. Can you find the closed loop system transfer function with this and tell whether the system is stable or not? K considered 1. So this becomes 60 by S into S plus 6 into S plus 2, S minus 3.6. Now this will become 60 into S minus 3.6 divided by S into S plus 6 into S plus 2 plus 60 S plus, sorry, minus. into 3.6. Not stable. Okay. S cube plus 8s square plus 12s plus 60s minus 60 into 3.6. So here itself we found that it is not stable because there is a negative term here, right? So this becomes s square plus 8s square plus 12s plus 72s minus some term. So this minus will give me, this minus will make the poles go to the right of the explain. That makes the system unstable. Right. It's correct. Okay. Right. A process with open loop transfer function g of s is equal to k e power minus s tau d by ts, capital Ts, time constant, plus 1 is controlled by PID controller. The options are, for this purpose, derivative mode, improvise transient performance, derivative mode, improvise steady state performance, integral mode, improvise transient performance, integral mode, improvise steady state performance. It's little twisted, but straightforward only. Twisted to interpret. So take your time, understand what the question tells, and then explain. I have a system with e power minus s tau d. That is a time delayed system. So I have this represent this form of a system where I say the derivative mode improves the transient response, derivative mode improves the steady state response, or integral mode improves transient and steady state. So which one will go well with this? Which improves what? Excuse me. We can find it with that keyword we know, no? Derivative doesn't have any action in steady state part, right? So with this, we can rule out this. If this is being ruled out, integral will improvise the steady state, while derivative will improvise the transient responses because it brings down the overshoot and it reduces the rise time So, and it makes the response faster. So comparing all these things, derivative will improve the transient response while integral mode will improve the steady state performance. I hope this is clear. If you have any doubt, please let me know.
No
Next,
problem.
yeah,
Thank you.
thanks. Okay. Next question is a PID controller is used to compensate a system compared to the uncompensated system. The compensated system has higher type number, reduced damping, higher noise amplification, larger transient overshoot. So I'm making all this statement based question to let you understand the nature of the PEPI, controllers. So try to go along with that so that it will be useful for you to learn about it. Initially, it will be little confusing which increases what or which reduces what. But if you practice around it, it will be easy for you. Can you guess? A PD controller is used, no integral, only P and D controller is used to compensate a system, some particular system. Compared to the uncompensated system, the compensated system has which of this below behavior. Also, we saw it's the keyword we learned in while learning that box table.
Type number would increase.
Okay. Other than that, anything you think?
Noise amplification also increase because of derivative.
Exactly. That is the actually correct answer because type number will be dependent. Not derivative won't always increase the type number. But noise amplification is a very important problem because if that uncompensated system has noise, it will change rapidly. Noise won't be constant, right? So it will change rapidly. So when you take a derivative or base depending on the rate of change of the noise, your derivative action will also change rapid and it will be large. So noise amplification is a very big problem when you comes to a derivative control. It's a like basic understanding behind it.
Yes, ma'am.
Right. I'll just add one more question and we'll wrap up this session. I'll make a statement. Let me know whether this is true or false. Adding a zero to a closed loop system close to the origin on left hand side increases the rise time of the system. Think properly and answer. Don't rush to answer. Statement A true, statement B false. Adding a zero to a closed loop system close to the origin on the left hand side, not right hand side, close to the origin on the left hand side. Consider minus zero point 0.1, minus 0.5, minus 1, whatever, but close to the origin increases the rise time of the system. We saw this during the live session when we discussed the transient response. If you recollect, you can check with your notes or something. False. Why so? Why do you think it is false? Correct. Very good. So adding a zero to a closed loop system will initiate faster response, and this faster response will result in the decrease of the rise time. So increasing the rise time is the false statement here. So zero will make this system work faster. That's why adding zero means adding a derivative control, right? Because when you take a Laplace transform, d by dt of something, you will get kd into s. So this is like adding zero at the origin. Similarly, this I'm that's why I made a statement that adding zero at the origin, nearly to the origin. So kd into s, my s plus 0.01, I'm considering this as kds. So this is actually a derivative control. Adding zero to the closed loop system close to the origin is a derivative control. So derivative control in general improvises the response, or it make the system faster, while integral response makes it slower, right? So this makes it faster. So if the response is faster, your rise time will automatically reduce when compared to the uncompensated system. That's why the statement is false. Okay, right. If you don't have any doubt, we can wrap up this session and leave. You can leave.
Thank you, ma'am.
Thank you. Thank you.